All right, so again, we said we're looking at a velocity graph here, okay? So the first question is, how fast was the rocket climbing when the engine stopped? What'd you guys say for that?
That's probably the 2.
190.
Okay.
190 feet per second.
190 feet per second, right? Okay, right? Because this is the velocity graph, okay? So it would be climbing the fastest when the velocity is its greatest, right? When it's the highest. So that would be at 190 feet per second. It says, how many seconds did the engine burn? 2, right? Because that's the length of time it took me to go from there to there, to velocity at its highest point. When did the rocket reach its highest point, and what was the velocity then?
8 seconds.
Okay, it was at 8 seconds, and its velocity at that moment was 0 feet per second, right? So does everybody agree? And again, this is one of those weird things. You're very accustomed to looking at time position graphs, not time velocity graphs. So from 0 to 8 seconds, velocity is what? Well, it's positive. It's positive, right? And anytime velocity is positive, we're moving in a positive direction. In this particular problem, we would be moving up, right? Okay. And then why is the velocity 0 right then? Okay, and what's it going to do? It's got to come back down, right? So you have that momentary time where the velocity is actually 0. When did the parachute pop out? And how fast was the rocket going then? Yes, yeah, 90, it would be going at 90 feet per second. Falling, well, you either negative 90 or falling at a rate of 90, right? Because that it was, and what did you guys say here?
About 11.
Yeah. So when did it pop out? Yeah, I think I said about 11 seconds. Okay, and it was falling at 90 feet per second. Now it says, how fast is the rocket falling? You wouldn't say falling at negative 90, right? You would say falling at 90. How long did the rocket fall before the parachute opened?
3 seconds.
Yes, about 3 seconds, right? Okay, the next one, when was the rocket's acceleration the greatest?
At 2 seconds.
Like just before, like right at that 2 second mark, right? Okay, sounds a lot like a limit. 2 from the left. Okay, so about 2 seconds. And when was acceleration constant? From 2 to 11 seconds, right? Okay, because that's your acceleration curve, so 2 to 11 seconds, something like that. Okay, so so let's think about this. All right. So here's my parachute, or I'm sorry, my rocket. It's been shot up by that engine. It's still going up, but it's going up at a slower rate. And then here it starts to fall, and then all of a sudden a little, whatever it said, some kind of little parachute pops out. And so what's it doing right here? It's still what? Falling, but it's falling at a slower rate because the velocity is actually higher. Okay? So it sounds like you guys have a pretty good grip on that. We need to summarize some things that are happening in this problem, and we need to talk about the calculus involved here. Okay, in calculus, S of t is going to represent a position function, the position function that we're dealing with. Okay, S of t will be the symbol that we use to represent the position function, or your textbooks will use that more often. What is the rate of change in position?
Velocity.
Velocity, right? Do you agree that the rate of change in position, because that would be distance divided by time, and that makes sense as a velocity unit, right? So how is velocity related to position? It is its derivative, right? That's v of t. Sorry, it just got closed up there. V of t is equal to s prime of t, and that's going to be my velocity function. So A of t is going to represent, what do you think? Acceleration. And tell me how acceleration is related to velocity. It is its derivative, right? Because it is, acceleration would be the rate of change in your velocity. So A of t will be equal to v prime of t, which I heard somebody say is s double prime of t. That's exactly
Can you
right.
explain the double prime?
That's taking
The second derivative.
Okay.
Yeah, so if it's the if velocity is the derivative of position and acceleration is the derivative of velocity, acceleration would be the second derivative of the second derivative of position.
How'd you find the second derivative?
You just take the
It's
derivative.
Yeah, it's the rate of
Take
change.
everyone at once.
It's just that it's exactly what we said here. Acceleration is it's the rate of change in velocity. Okay, and the rate of change in velocity is the rate of change in your position. So you literally just take, like if you started out with x squared, the first derivative is 2x, the second derivative is 2. You just continue down the line. Okay, and we said this is acceleration. Okay, so let's put, we'll just put some units here. If position was in feet, velocity could be in feet per second. And if that was the case, then your acceleration units would be what? Feet per second squared. Okay, and then I heard you guys talking about this just a second ago. How is speed? What is speed? What's the difference in speed and velocity? Okay, speed is always positive. It doesn't have directions. So we could define speed to be the absolute value of velocity. What about displacement? What do you remember about displacement? Very good. It is the distance between the initial position and the final position. So if you run one lap around the track, what's your displacement? 0, right? Where you started and where you ended was exactly the same. All right, we alluded to this a while ago. If velocity is greater than 0, what can you tell me about your particle?
It's moving.
It's moving. How's it moving? It's moving in a positive direction. And what are some words that could describe that? If we're moving in a positive direction, up, right? Up, right.
Like north, south, east, and west.
Okay, yeah, possibly. It would depend on how the wording was set up. How about we stick with up, right, and forward? And then similarly, if velocity is less than 0, then we're talking about moving in a negative direction. So the corresponding words there would be what?
Backwards.
Down, left, and backward, right? Okay, so one other concept we need to take away from this picture right here. We need to talk about, we've talked about how this particle, or we've talked about the direction in which the particle is moving. But the other question that you can be asked about in a problem like this is whether the particle is, or whether your parachute or particle, AP likes to talk about particles a lot, so sorry if I go there. Whether this parachute is speeding up or slowing down. Okay? I want to know whether it's speeding up or slowing down. Well, let's just talk the rocket. Sorry. Okay, the rocket. Sorry. Okay, so let's talk about the rocket here. What's it doing right here? Clearly. It's speeding up, right? Okay, we all understand that. What's it doing here to here? It's slowing down. Right here it reaches its maximum height, right? Talk to me about what's happening here. It's speeding up, right? It's just speeding up in the negative direction. And then tell me what's happening here. It's slowing down, right? Okay, so I think we have a feel for that. Let's talk about velocity and acceleration in all of those situations. Okay, so let's talk about this first piece of the rocket flight. The velocity here is what? The velocity itself has what kind of values? Positive, right? Those are positive velocity values. What about the acceleration here? It's positive. How do you know that? Because acceleration is the derivative of velocity. So I would be looking at the slopes here, right? I just want to make sure you know what you're looking for. I'm looking at the slopes, and the slopes here are positive, so acceleration is positive. So velocity and acceleration were both positive here, and what was the particle doing?
Accelerating.
The rocket? No. Speeding up, right? Those are the question. That's the question that we're talking about. You have to be really careful with that because of what we're going to talk about next. Okay? All right. So now, what did you say the particle was doing from here to here?
Slowing down.
It's slowing down. Talk to me about velocity. It's still positive, but talk to me about acceleration. It's negative, right? Acceleration is negative. So velocity positive, acceleration negative, particle slowing down. Okay? Here, what kind of velocity do we have? Negative. Those are negative y values. And what kind of acceleration do we have? Negative. I mean, like, look before you just randomly answer, people, okay? Like, this has a negative slope, right?
Yeah.
And acceleration is derivative of velocity. So here to here, velocity is negative. It has negative y values. And the slope of the velocity curve from here to here is also negative. And what'd you tell me that the rocket's doing? Speeding up, right? Okay, so now let's look right here. Velocity is still what? Negative. Acceleration is positive. I would put that phone away for right now if you can't stay like focused here. Oh, okay. So you're even more like zoned out. Okay. Velocity is negative, but acceleration is positive because it has a positive slope. And what was it doing? It was slowing down. Okay. So what can you summarize from our discussion there? If velocity and acceleration have the same sign, then whatever it is I'm talking about, my particle will do what?
Speed up.
Speed up. But if my velocity and acceleration have opposite signs, it's going to slow down. Okay? So that's the last thing that we need to summarize here. Speeding up versus slowing down. By the way, you will have at least one, if not more than one, question on the AP test that asks you whether something is speeding up or slowing down. And the way that you justify your answer in order to get credit is by doing exactly what we did here, talking about the signs of velocity and acceleration. Okay? So if V of t and A of t have the same sign, what am I doing?
Speeding up.
Speeding up. If V of t and A of t have different signs, then yes, we are slowing down. So one more time, if you're asked on an AP test whether something is speeding up or slowing down, you would say, for example, it is slowing down since A of 2 is positive and V of 2 is negative. Okay, you would have to state the velocity and the acceleration at whatever value t is and show that those signs are either different or the same. Okay, you with me there? All right, take a look at this problem. So for once, you guys are going to be behind the other class. I got to hurry. So a particle moves along a line so that its position at any time t greater than or equal to 0 is given by, there's a position function, right? S of t, where S is measured in meters and t is measured in seconds. Find the displacement of the particle during the first 2 seconds. You told me that displacement was final position minus initial position, right? Or the difference in those. So S of 2 is negative 1, right? Negative 4 plus 3 negative. Yeah, negative 1. And then minus S of 0 is 3. So your final position is negative 4 meters. What's that mean? Interpret that.
4 meters away from the start.
Okay, and I guess to the left or behind or whatever you want to say. Yep. Okay, now I want you to look at B and C before we answer them. B says find the average velocity of the particle in the first 4 seconds, and C says find the instantaneous velocity of the particle when t equals 4. Instantaneous velocity would indicate that you need to do what? The derivative, right? The derivative. So V of t, tell me what V of t is equal to in general terms.
Derivative of this.
Okay, and then tell me what it is.
2t.
2t minus 4, right? And then I want it at time what?
4.
4? So what's that equal? 4, what are the units?
Meters per second.
Meters per second, right? Okay, so go back to B. B wants the average velocity. What do you think you would do there?
Find the endpoints or the
Okay,
0 hit 4.
so how about S of 4? That would be my position at 4 minus S of 0 and divide it by what?
2,
Ooh, how about 4 minus 0? Not 2.
4.
2 would give me a what? It's like the...
Wrong answer.
Yeah, it would give me the wrong answer, right? I need the average rate of change here, right? I need the average velocity. Average rate of change is just regular old slope formula. So S of 4 is 3. S of 0 is 3. So what's the average velocity here?
0.
0. What's that mean about the function? It must be what?
It didn't move at all from, or I mean, it's first.
You got it.
Never mind.
Cosine.
It's symmetric, right?
Yeah.
Means it would be symmetric. There'd be some symmetry there of some sort. Okay, I know we're going to run out of time here pretty quick. D says find the acceleration of the particle when t is equal to 4. Find the acceleration when t is equal to 4. Well, what do I need to do to get the acceleration in general terms? The derivative of
The velocity.
velocity, right? What is the derivative of velocity? 2. And then I need the acceleration at 4. But what I just found out is that it's constant. Okay? So, I did not have time to talk about E with you, which is a pretty interesting discussion to look at those things on the graph. So either touch base with someone in the other class period over it, or I'll talk more about it next week. But here's your homework on this stuff. Page 136, 9, 10, 19 through 21. That's in your textbook. Okay, so that's your homework over 3.4, and then this is your test review, which I sent to you in a remind. And I hope you guys have a great weekend.
So 4 parts.
Well, they all have multiple parts. And they all have multiple parts. They're kind of like this.
You guys are leaving early, right?
For what?
For volleyball?
No.